Hey everybody, here's the second part of the review for Unit 8 in Calculus. Let's go ahead and get started. We're going to be focusing on the free response questions now. Question number 19 has a picture, graph of two functions. One is a polynomial function. Let's see if I can do a good job of this. And then the other one is a line. And that line is supposed to be tangent to the polynomial. So it said that this is f of x, and then this is line L here, okay? And this is region R and region S. So for part A, it says show that L is tangent to the graph of f at the point x equals 3. So for part A, all we have to do is basically find the tangent line of this curve, f of x, and show that it is equivalent to that line. So remember, the first thing we need to do in finding a tangent line is to find the slope, and then the second thing we need to do is find the point. So let me start here. We know that f of x is given as 4x squared minus x cubed. We need to take the derivative of that because we're trying to create the tangent line. So the derivative is 8x minus 3x squared. And then it says show that it's a tangent line at x equals 3. So we need to plug in 3 to f prime. So 8 times 3 minus 3 times 3 squared. That's 24 minus 27, which is negative 3. So we have our slope now. We have our derivative at x equals 3. We need to figure out our value of the function when x equals 3. So we're just going to take 3 and plug it into our original function. So that's 4 times 3 squared minus 3 cubed. And then from there, simplify that. So we got 9, we got 36 there, 27 there. So f of 3 is 9. So our tangent line is going to be y minus 9 equals negative 3 times x minus 3. And we need to convert that so it looks like the tangent line or the equation of the line that they gave. So that's y minus 9 equals negative 3x plus 9. And so y equals negative 3x plus 18. And the way they wrote it was backwards here. So they said 18 minus 3x. And so we have our answer there. All right, so that's part A. Part A was worth 2 points. You would have gotten 1 point if... let me write it over here. You would have gotten 1 point if you got f prime of 3 and f of 3. So showing that both of these values, showing these values at x equals 3, and then you would have gotten 1 point for creating the tangent line. So getting to show the work at plugging those in to show that that's the actual tangent line. So 2 points for part A. For part B, it's asking us to find the area of the region S. So we're trying to find this region here. Let me go ahead and shade it in. We're trying to find this region. Now, there's a couple ways to go about this. We could split it. Let me get a different marker here. We could split it at this point and go up, and then take two separate integrals. So we could have found the integral of this, or the area of this region, by finding the integral of the upper curve minus the integral of the lower curve, or the integral of the upper minus the lower. And then we could have found just the integral of the line here, or find the area of that triangle. That's one way of doing that, and then adding those up. The other way, and I think this way is a little bit simpler, is to draw a line straight down from the point of intersection here. And if I can find the area of this big triangle, and then subtract the area of this region, we would have the area of the green region, and that's what we want there. So the first thing we have to do in order to do that is figure out what this point of intersection is, what this point is, and what that point is. So we have to go through a few pieces of work here. So the first thing we're going to do is to find the point of intersection. And so to find the point of intersection, we're going to set the two equations equal to each other, the two functions equal to each other. So we're going to say 4x squared minus x cubed equals 18 minus 3x. And because we have a calculator here, this is stored as y1, This is stored as y2, so we're just going to find the intersection using our calculator. And that intersection is x equals 3. So we have the point of intersection. We need to find this point here, and that's going to be when the polynomial equals 0. So we're going to set that equal to 0. And we end up with x equals 4 there. And then this last point is setting the line equal to 0. So that would be 18 minus 3x equals 0, which makes x equals 6 at this point. So we know all three of those things. And so now we've got to figure out the equations that represent these different areas. So the region S, I'm going to use some notation here. The area of region S, remember this is region S, is equal to the area of the triangle, the big triangle here, minus the area, and because I have it colored here, I'm going to say the area of the red region. Okay, so we'll just set up equations that represent that. Well, the triangle, the area of a triangle is 1/2 base times height. So the base of this triangle is the distance from 3 to 6, which is 3. And then the height of this triangle is the value of either the curve or the line when x equals 3. So all we have to do is plug in 3 to our line here. And so we get 18 minus 3 times 3, and that's 9. So this expression represents the area of the triangle. Now we need to figure out the area of the red region. Well, the area of the red region is kind of has a curvature to it, so we're going to take an integral there. So it's going to be the integral from 3 to 4 of f of x only, because that is the only function that's bounding that region. So f of x was 4x squared minus x cubed, and then dx. So the solution to this will give me the area of the region S. So this is 27 over 2, which is 13.5, minus, you take the integral by just plugging in your calculator there, you get 5.583, and then your final answer here is going to be 7.917. And so that is your region, the area of region S. As far as points go for this, this part is worth 4 points. Okay, the first part, or sorry, the first 2 points are given by an integral expression. So if you have this right here, that's worth 2 points. So you're going to get 1 point for having the correct limits there. Okay, 1 point for the limits, and then 1 point for having the correct integrand. All right. You would get 1 point for the area of the triangular region, so the 1/2 3 times 9, and then 1 point for the final answer. So 4 points altogether for part B. Okay, that's a pretty straightforward one, but it is one where you have to chop it up a little bit. So that's part B. Part C talks about the volume after we revolve the region R around the x-axis. So what I need to do is look only at region R. We're revolving region R around the x-axis. So the line in part C doesn't have anything to do with the problem, and neither does region S. So we can get rid of all this, and we're just taking this region R and revolving it around the x-axis. So I'm going to draw my axis here, and then we're going to revolve that around there. So you remember, to find the volume of a region when I revolve, it's either going to be one of two things. It's either going to be the disk method or the washer method. In this case, as I revolve this, I'm not going to get any gaps or holes here. I'm just going to get something that looks like this on the other side, and then those are my revolutions as my marker's completely dead here. So let's see, we're going to get revolutions here, okay? You can see the cross section's a circle. Now the question then is going to be, what is the radius? The radius is the distance from the axis up to the curve. So this region, or this length, is radius R. Probably shouldn't call it capital R because they already called it capital R, that region. So I'm going to just represent that as R. R is the radius. So we're going to say the radius here is the function f of x, which is 4x squared minus x cubed. All right. So we notice that this is a disk because there are no gaps. So then we can say the equation is, for volume, is pi times the integral from 0 to 4, we already figured that out earlier, of the radius squared, and then dx because we're perpendicular to the x-axis. So since the radius is represented by this, we could say pi times the integral from 0 to 4 of 4x squared minus x cubed squared dx. And so that's the setup, and that's the majority of the points, honestly, right there. The last point is going to come from the answer. So one thing I want to make sure you're clear on, when you're typing this in your calculator, a lot of students just make mistakes by forgetting to multiply by pi. So what I do is I keep that pi there, and then I just type in the integral expression, which is results in 156.038. And then I'll multiply that out. You actually don't need to multiply it out there. You can just leave it like that. But if you do, it's 490.208 as your final answer. So again, this is a disk because there are no gaps. So it's going to be the integral of the area of the circle times the height. So there's your pi r squared times your height. That's the area of your circle times your height, which gives you the volume of each individual cylinder. And then we're summing all those up. As far as points go, you're going to get 1 point for having the correct constant and the correct limits. Okay, 1 point for having the correct constant and the correct limits here. So if you put that pi inside, as long as it's outside the parentheses there, that's the constant, and then the limits are going to be obviously the bounds there. You're going to get 1 point for the correct integrand expression, so 1 point for having 4x squared minus x cubed all squared. If you said f of x here squared, that would be okay too because they labeled it as f of x. And then you're going to get 1 point for your final answer. So that's number 19 as a whole. This is part C. So there's that. Okay, for number 20, this is a pretty straightforward problem here. We have a shaded region that's bounded by the curve f of x and g of x, and I've stated the two functions here. They even gave you our intersections from 0 to 1, so that should be pretty straightforward. Part A says to find the area of the shaded region. So that should be pretty straightforward. Remember, it's always to find the area that's bounded by two curves, it's always the integral of the upper curve minus the lower curve. And the reason that's true, or the reason you can see that, right, it's the integral of the upper curve minus the lower curve, and then dx. We'll talk about limits and plugging all that in a second. But the reason that's true is because the integral of the upper curve is going to be a positive answer. The integral of the lower curve is going to be a negative answer. So when we subtract a negative number, that turns into adding a positive number. And so when we add this area with this area, we get the total area. But because we're taking an integral here, that produces a negative number, so we subtract that, and it turns into adding a positive. But still, the general rule is always the integral of the upper curve minus the lower curve, and you got your answer. So it's going to be the integral from 0 to 1 of the upper curve, which is f of x, minus the lower curve, which is g of x. And I can state it like this, and it's fine because they stated that these were f and g. If they just said this curve is represented by y equals 2x times 1 minus x, you would need to type that in there. But your final answer for this is going to be 1.133. So that's part A. All right, as far as points go for this is a 2-point problem. You're going to get 1 point for having the correct integral expression. So basically 1 point for this line right here, and then 1 point for your answer. So that's part A. Okay. All right, for part B, it says find the volume of the solid generated when the shaded region enclosed by the graphs f and g is revolved about the horizontal line y equals 2. Well, first thing we want to know is that y equals 2 is somewhere up here, and we're revolving this region around that axis. And so as you can see, as we revolve it around that axis, we're getting a big hole inside of that, which means we have a washer here. It's the washer method. And so if you remember, the washer method says that volume is equal to pi times the integral of big R squared minus little r squared dx in this case, because we're revolving it around a horizontal line. Our bounds are going to be 0 to 1. And so there's our volume expression. The big question is, what is big R and what is little r? And so remember, to figure out radii, it's the distance from the axis to the curve. Normally our curve is on top of the axis. In this case, the curve is on the bottom of the axis. There's nothing wrong with that. The question is, which is the correct value? Should it be the axis minus the curve, or should it be the curve minus the axis? It's always the upper thing minus the lower thing. So big R is going to be the distance from the axis all the way down to g of x here. Okay, that is the big radius. As I take this object and I revolve it around y equals 2, the distance from here to here is going to be the radius of the outer thing. The inner thing, the inner circle, is going to be the distance from the axis to f of x. So we're going to say that big R is going to be 2 minus g of x, and little r is going to be 2 minus f of x. And then all we have to do is plug that in, and we'll have our volume. So volume equals pi times the integral from 0 to 1 of 2 minus g of x squared minus 2 minus f of x squared, and then that'll all be in brackets dx. So that's a pretty long, gross expression, but if you break it up into parts, you can see it a lot easier. Remember, it's the washer method, so there's a hole there. So it's pi times the integral of big R squared minus little r squared, and big R is the distance from the axis to the curve. So 2 minus g of x. If you said that big R was g minus 2 of x, or sorry, g of x minus 2, you would be okay as long as you're consistent with your little r. So if you said f of x minus 2 there. But if you say one is g minus 2 and the other one is 2 minus f, you're kind of being contradictory, and so they're not going to give you full points for that. So anyways, the final answer here is going to be 16.179. As far as points go, this problem is worth 4 points. You're going to get 1 point for the limits and the constants. So what that means is you're getting 1 point for pi and the integral from 0 to 1. You're going to get 2 points for having the correct integrand. Now, correct integrand being everything inside the integral here. So if you showed that you understood that it was a washer, then that would be one of the points. And then if you had the correct radii, that would be the other point. And then, of course, 1 point for the correct answer there. All right. All right, so for part C says, let h be a function given by this. So I'm going to write down h here. H of x is equal to kx times 1 minus x. All right, so it says that we have this extra function here. And it says for each k greater than 0, the region not shown enclosed by the graph of h and g. So in part C, we're not even looking at the graph of f anymore. So I'm going to go ahead and erase the curve of f and the statement for f, because we're not even looking at f anymore. Now, it says that h was not represented in the graph, but we can kind of get a feel for what that is. If I distribute this in, we can see that this is going to be kx minus kx squared. That's going to be a parabola that opens down, and then the x-intercepts are going to be 0 and 1. So we actually have a parabola that looks very similar to f, but maybe it goes higher. That'll all depend on k, the vertical stretch. But this now is the curve h of x, whatever that is. We don't know how high it goes or how low it goes, but we do know that it opens down and it has these x-intercepts, so it has to be above the x-axis there. So that is the graph of h. And then it says that the region that's enclosed by h and g is the base of a solid with square cross sections that are perpendicular to the x-axis. So we have cross sections. So if I slice this in such a way that it's perpendicular to the x-axis, this is the base of a square cross section. So let me go ahead and draw one square cross section here. So the idea in finding the volume of this region or this solid, remember, is always, whether you're talking about discs or washers or cross sections, the volume of any object is going to be the integral of the area expression. So in this case, we're going from 0 to 1 because our bounds are 0 to 1 and we're perpendicular to the x-axis. And because we're perpendicular to the x-axis, it's going to be in terms of x. So we can figure out the volume as long as we can figure out the area expression for that cross section. Well, the area of a square is length times width, and the length is dictated by the distance from one curve to another. So the distance between these two curves can be written as h of x minus g of x, and that would indicate that the height is also the same thing because it's a square. So then we can say that the area of this square will be h of x minus g of x all squared. And so all we have to do is take that and plug it into my integrand. And so we have volume equals the integral from 0 to 1 of h of x minus g of x all squared dx. So there's my volume equation. Now, this problem goes a step further. It says there is a value of k for which the volume of this solid is equal to 15. Write but do not solve an equation involving an integral expression that can be used to find the value of k. So the first thing I note in my equation is that I don't have any k's in here. So instead of writing it in in function notation form, I'm going to have to replace these functions with the actual expressions that they represent. So we're going to say volume equals the integral from 0 to 1 of, well, h of x is kx times 1 minus x, and then g of x is going to be 3 times x minus 1 rad x. Okay, so that is h minus g. We have to square it, and then dx. So now I have a volume equation that has k in it, so I can solve for k. And then it also said that the volume is going to be 15 at some point. So I'm going to set the volume equal to 15. So there is an equation that when solved, you're going to figure out what x is. All right? Now, point values here, you're going to get 2 points. 2 points for the correct integrand, and 1 point for your correct equation or your correct answer. And that would basically mean if you set up an integral expression, an integral, and set it equal to 15, you're going to get the 1 point for the equation, and then 2 points for the correct integrand, meaning that you had the correct, you identified that the area of the cross section is a square, so you're going to have something squared here. That's probably going to give you 1 point, and then 1 point for what's actually inside the squared there. All right, so that's the end of number 20, and so that will be the end of the second video for the Unit 8 review.